Welcome to Chem We Talk, a channel where we're not afraid to talk about any chemistry topic. In today's video, we will go over how to determine if a reaction has reached equilibrium. For that, we will introduce the concept of reaction quotient, also known as QC. Okay, just a quick overview of how we're going to break down our video. We're going to start by reviewing the definition of chemical equilibrium, but if you haven't, please check our previous videos on rate laws and also on chemical equilibrium. Then we're going to go over the difference between dynamic and static equilibrium. After that, we're going to define what is the reaction quotient, QC, and then eventually we're going to go over how to use QC and KC to predict if a reaction has reached equilibrium or not. Okay, so this here is a similar slide from the previous video that's on the description below, but let's just start by looking at this reaction. We have A, B going to C and D. We have an equilibrium arrow, and we remember those are elementary reactions, right? You have an equilibrium arrow. So from the previous video, you also saw that equilibrium just means that the rate of the forward equals the rate of the reverse reaction. And if you remember the rate law video as well, we can write the rate of the forward reaction as just a Kf arbitrarily times the concentration of A raised to the coefficient. And again, we can only raise to the coefficient because we know that this here is an elementary reaction, which is a reaction that only occurs in one step. Then you have B to the B equals to the K of the reverse reaction, so going from right to left. And now C to the C, D to the D. If I just do some reorganization of my equation, let's just keep Kf on the left side of this equality and just divide both sides by Kr. So Kr goes to this side, and then we're going to keep C to the C, D to the D on the right, and we're going to divide everything by A to the A, B, to, B over raised to B. And we get this equation here that's very famous, and we just usually read this as the products of reactants, but in fact that's just like the products of the products raised to their respective exponent divided by the reactants multiplied by reactants raised to their respective exponent. And that is our equilibrium constant Kc. Okay, just a quick review. Don't forget that no solids or pure liquids are included. The explanations are beyond the scope of this class, but has to do with the concept of activities. Okay. One thing that's very important is that the rate constants for a given reaction are temperature dependent, which means that your Kc will also be temperature dependent. So the only thing that will change your K constant will be temperature. Okay, so now we have the definition of equilibrium, but let's try to visualize it in a more empirical way. Let's use a simpler reaction, which is A going to B, and then B going back to A, which is an equilibrium. Those are both aqueous species, so they're both included in the equilibrium expression. So if I were just to calculate my Kc, it would simply be B raised to 1, because there's no coefficient in front of it, divided by A to the 1. But let's say that we don't know what the value is. We're going to do an experiment, and let's suppose that we have very powerful magnifying glasses that could look at the composition of the reactants in a beaker. Okay, so I'm just arbitrarily picking this temperature 290, and at T equals 0, in my 1 liter flask, I have 5 A's. Let's just represent those as moles, right? So we have concentration, but we can use those as simple molecules as well for the sake of our argument. Okay, so at T equals 0, we have 5 A's. At T equals 3 minutes, we can see that the composition changed. Now we have 4 A's and 1 B. And if I let it a little longer, 30 minutes, we see that now we have 3 A's and 2 B's. And that just exaggerate a lot. I know that's like redundant, but let's have like 1 million years have gone. And now we have 3 A's and 2 B's. Okay, so the only reason why I use this time is just to say, okay, that's been so much time that there was enough time given for the equilibrium to be achieved. But there are some reactions actually in real life that actually might take longer to reach equilibrium. But that's for the sake of argument, we know that we are already at equilibrium at 1 million years. So if I would ask you, when was equilibrium first achieved in this reaction? And the answer is at 30 minutes, right? You can see that at 1 million years, in our case, I said that we were at equilibrium, right? And this composition, in configuration, we had 3 A's and 2 B's. But at T equals 30 minutes, we already had that configuration, 3 A's and 2 B's. So the equilibrium was first achieved at 30 minutes. Okay, so we can actually calculate my Kc expression, right? Because now we know that at equilibrium we have 2 B's, which is my products, and then 3 A's, and we get 2 over 3 or 0.67. That would be my numerical Kc value. So for any given reaction that has only A and B at 290 K, if I do products of reactants, I would always get 0.67. Okay, that's what the equilibrium constant means. Now let's go to a different concept. Is this equilibrium static or dynamic? And static, if you don't recall it, just means that something that's not moving, and dynamic is related to movement, so it's something that's actually going on. So if we compare beakers at 30 minutes and 1 million years, we can see that A, for example, became B from left to right. This A also became B, but at the same time, this A went back and react to form B, and this A also went back to react to form B. So that means that at equilibrium, there are still reactions going on, but the concentrations are not changing. So therefore, this here is a dynamic process. Okay, so important point, at equilibrium, chemical reactions still occur, but the rate of the forward and reverse reaction are the same, right? That's the definition of equilibrium, so there's no change in the concentration of products and reactants. So if you're just looking at a beaker with normal glasses, you will not see any difference in the composition. All right, let's do now a challenge question. Okay, so we are still using the same system. We have A and B, the same reaction, same temperature, same Kc. But now, instead of starting with 5 A's, I'm going to start with 5 B's. And let's give it some thought. And what would the beaker look like now at equilibrium? Okay, so for now, I'd like to stop the video and give some thought, think a little bit, and then resume the video once you have an answer. Okay? All right, so hopefully you gave some thought about it, and now you're divided between probably one of those two candidates, right? So one option would be you get a beaker with 3 B's and 2 A's, or the other option is you get 3 A's and 2 B's. And remember, in the first case, I think we got 3 A's and 2 B's, right? So I know you might feel tempted to say that, okay, when I start with 5 A's, I end up with 3 A's. So if I start with 5 B's, I'm going to end up with 3 B's and 2 A's, right? Intuitive, that makes sense. However, that is not the case. You're going to get 3 A's and 2 B's again because of the Kc. So the equilibrium, I like to say, is like a law of nature. Every time you're going to have A and B, as long as you are in the same temperature, you're always going to get products of reactants being exactly the same. You're going to get 0.67, so 2 B's and 3 A's. Okay, but it might not be very intuitive to see it, so let's use some of the concepts we discussed in the previous video to see if we can make like a mathematical approach. So it doesn't make much sense to write this reaction A going to B if we start with only B, right? So it would make more sense to write the reaction as B going to A. In that case, if you remember, if you flip a reaction, your Kc value will also flip, right? So you're going to have, instead of having 2/3, you're going to have 3/2. So, and if you look at here, you're going to have 3 A's and 2 B's, all right? All right, so now we're going to introduce the concept of reaction quotient, which is going to be used to determine if a reaction has reached equilibrium or not. Okay, so let's go back to our first scenario. But let's pretend that, yeah, we know that this here was at equilibrium, where we got 2/3 as being our Kc, so 0.67. So you did this experiment yourself, and you at 290K, and you calculated. But now a friend of yours will try to do something different. You're going to remove this first beaker, the last one too, this one too, and your friend would only get to see this beaker. And you can ask him, is this reaction at equilibrium? We know it is not, right? Because you would need to be at the 30 minutes range. But how would someone predict if this reaction is at equilibrium or not? Okay, so what we're going to do here is introduce the notion of reaction quotient, or QC. And the letters QC reminds me of quality control. So the reaction quotient QC would basically be a quality control for you to determine if the reaction is at equilibrium or not. And the formula is going to be exactly the same. It's going to be products over reactants raised to the exponent. But the only difference is for the Kc, you know that those are the concentrations at equilibrium. And here you don't know. So when Qc equals Kc, you are at equilibrium. But once Qc is different than Kc, you are not at equilibrium. So let's calculate in our case here, this 3-minute scenario. Qc is going to be still products over reactants, which in our case is going to be B over A. And again, please remind that this here is a very simple reaction with coefficients 1 and 1, so it's very simplified for the teaching purposes, but we're going to go over later problems where There are exponents involved that are more complicated, but here you're just going to do b over a, which is going to be 1b divided by 4. It's going to be 0.25, and that's my q. Once I compare my q to my k value, you see that q is much smaller, which means that we have more reactants than at equilibrium, or more reactants in this scenario than we should have, right? Because if this number is smaller and the formula is products over reactants, to make this number go up, you need to increase the amount of products or decrease the amount of reactants. Okay? And once we look at our scenario, we had at 3 minutes 4 A's and 1 B, and we know that at equilibrium we have 3 A's and 2 B's. So because we have more reactants than we should, the reaction needs to move to the right, or go from this A needs to react to form 1B to reach equilibrium. Okay, so just like a quick summary, when QC equals KC, the reaction is at equilibrium, and the reaction does not move, so it just stays what it is. QC, it's smaller than KC. We have more reactants than at equilibrium, or we have less products than we should have at equilibrium. So the reaction moves from left to right to make more products and consume some reactant. When QC is larger than KC, it's the opposite. Now we have less reactants than we should have at equilibrium, or we have more products than we should have at equilibrium. So the reaction now needs to move from right to left to consume some products and make more reactant. Just want to remind that because we have a dynamic equilibrium scenario, remember, even when QC equals KC, there are still reactions going this direction and that direction, but there's no net movement because the rate of this reaction is equal to the rate of that reaction. All right, well, let's look at one practice problem. Still using the same scenario, but now we're going to start in 3 cases. One case where we have 15 A's and 12 B's, 6 A's and 1.5 B's, 21 A's and 14 B's. So let's start with the first one. My QC in this case would be B over A. Again, it's the same situation, same scenario. It's going to be 12 divided by 15 now, and that is 0.8. First thing we notice when we compare it to KC is that QC is different than KC, which means that we're not at equilibrium. But will the reaction shift to the right or to the left? Now we need to compare. 0.8, which is our QC, is greater than 0.67, which is our KC. So that means we have more products than we should have at equilibrium, which means that the reaction needs to move from right to left. So some B will be consumed to form more A. So go to the second scenario. We have 6A and 1.5 B. So our QC expression is still the same. Now we have 1.5 divided by 6, which is 0.25. One thing we can notice again is that those numbers are different, which means we are not at equilibrium yet. And because now 0.25 is less than 0.67, we have more reactants than we should have at equilibrium. That's similar to the case we just went over. So now the reaction would shift from left to right to make more product. And lastly, we're going to calculate in the case of 21A and 14Bs. Same equation, 14 divided by 21, 0.67. Now QC is exactly the same as KC, so the reaction is equilibrium. Again, there are some A going to B, but there's also some B going to A at the same rate, so you don't see any difference. Okay? All right, let's now go from A's and B's to the actual reaction. So now we have at T equals 100 C, we have this N2O4 gas going to 2NO2 gas with a Kc of 0.21. And now the question is this reaction, or is this system at equilibrium at 100 degrees C if the concentrations of N2O4 and NO2 are the following? So every time the question is asking if something is at equilibrium or not, you need to remember right away that you need to use QC. Okay, so we know that Kc is products of reactants, and please be careful. Remember, we were using a very simple example where we had A and B, just 1 and 1 coefficient. Now we have a 2 in front of it, so we need to remember to put the coefficient on top. Okay, so QC equals NO2 squared divided by N2O4 raised to 1, and those are at equilibrium, right? And so when you are at equilibrium, when you do this products of reactants, you should get 0.21. But do we know for sure that we get this number in this scenario? We don't, right? So we need to plug in those numbers into the equation to see if we can get the same value. So I plug in here, NO2 is 0.7. So don't forget the square, and then we have 0.15. And we get this number here. And once we compare those two, we can see right away that those are different, which means that we are not at equilibrium. But more than that, we can see that QC is greater than KC, right? And once we look at the equation products of reactants, if QC is greater, that means that you have more products than you should have, right? So the reaction needs to go from right to left to consume some of those products and produce more reactant. Okay, all right. Let's just go here, a quick summary. Chemical equilibrium is a dynamic phenomenon, as we discussed, where the concentration of the reactants and products remain constant because the rate of the forward and reverse reactions are the same. Remember, there are still reactions going on from left and right, but because the rate is the same, you don't see any difference. Okay. The equilibrium constant for a given reaction depends solely on temperature. Okay, so for a given temperature, your Kc value will always be the same for the same reaction. Okay. And lastly, we can see we define the concept of reaction quotient, QC, which adopts the same exactly formula of the Kc equilibrium constant, but the QC can be used as a quality control by comparing it to Kc. So when QC equals Kc, the reactions are at equilibrium, so no change is observed. When QC is less than Kc, there are more reactants than you should have at equilibrium, so the reaction shifts to the right. When QC is larger than Kc, is the opposite scenario where you have more products currently than you should have at equilibrium, so the reaction shifts to the left, right, to consume those products. All right, thank you for watching the video. If you liked it, please make sure to subscribe to the channel, follow us on social media. I'll have our Instagram listed here. Please share the content with some of your friends, colleagues, and lab mates. Thank you, and see you in the next video. Bye.